Okay, we're continuing on chapter 11. We were talking about alkenes and alkynes last time, and we were talking about some reactions that they undergo, and they do addition reactions across the double bond. And basically, the idea of that is always sort of the same here. We're going to add basically something in to the double bond. It could be something like hydrogen, it could be something like water. It could be something like hydrogen and something else like HBr. But regardless of sort of what you're adding in, by the way, it could also be like two BRs if you like, two CLs. So whatever you're adding in will always sort of occur where the double bond is. As we talked about last time, we essentially need to make room for what's coming in. And that means that we have to get rid of the double bond. And absolutely, positively, nothing else changes. So as I mentioned last time, you essentially have sort of your answer on the left-hand side. You just got to do that sort of slight adjustment of obviously getting rid of the double bond to make it a single bond. Then obviously, depending on what you're putting on, uh, for example, we're putting two H's on. We do put it on again. Each carbon in that double bond originally gets one of those guys. Again, they do not get added to the same carbon, so everybody gets one on each side. Remember, though, if you are adding, as we talked about, hydrogen and something else, which is the case with water or HBr or HCl, it does follow Makartnikov's rule, which is if there is a difference when you look at the double bonds in terms of hydrogens, and in this particular case, we'll just do something maybe like that. And if we were adding something like water, again, not much changes, so still going to just make the double bond into a single bond, and that's all you got to do. Once again, just should copy exactly how it's written there on the left, turn that thing into a single bond. And in this case, though, whenever you add hydrogen and another element through this type of reaction, if there is a difference when you compare the number of hydrogens that are directly attached to the carbons that were in the double bond, then it actually does make a difference as to where you put the hydrogen. So if we look at the one on the right here, directly attached to that carbon in the double bond has two hydrogens. Over here on the left, this one has only one hydrogen. So the rule there is, Makartnikov's rule is the hydrogen will always go to the carbon that started with the most hydrogen. So in this case, we would actually put the hydrogen on the carbon on the right as it had more hydrogens to begin with. And that would mean that we would then put our OH on the other side there. And that would give us what is sometimes referred to again as the major product, which is typically what you want to draw. And when we do this reaction, which is known as a hydration reaction, we again go from an alkene to an alcohol. And again, that's how you kind of form an alcohol in this particular case. If we do the one up on top, which is known as a hydrogenation reaction, hydrogenation because we're adding hydrogen, we go from an alkene to an alkane, basically. Yes, single bonded. Any questions on those reactions? Yeah. Yeah, so hydration means basically water is involved, so it should be H2O. Hydrogenation is hydrogen. So yeah. So they'll call when you add H2 a hydrogenation reaction, and when you add water, they'll call it a hydration reaction. Yeah. Yeah. A halogenation reaction. Halogenation reaction is would be like one of these right here when you add something like HBr or Br2. So technically speaking, if we have the same guy or something like this, if you added like Br2, again, it works the same way. Just going to make the double bond into a single bond. And each of those carbons are just going to get a bromine in this case. And this is a halogenation reaction because we added basically two halogens from group 7, which is the halogens. So that's what's known as a halogenation reaction. When you do this one, this is sometimes called a halogenation reaction because you're adding hydrogen and a halogen together. So they'll sometimes call, if you added the HBr, a hydrohalogenation. And again, the hydro part of it means you're adding a hydrogen, and the halogenation part means you're adding a halogen from group 7. Yeah. But again, it goes on. This one you don't have to worry about because it's a symmetrical. So again, they're both getting the same thing. So it doesn't matter where you put it. They're both going to be the same. This, like HBr, would be the same sort of rule you would want to follow with water if there was some differences in the hydrogens to begin with. Other questions? Okay. So I want to try this one here. What would be the product here of this reaction? And if it says hydrogenation, you're adding basically H2. If it says hydration, you're adding water, HOH. If it says halogenation, you're adding somebody from group 7, two of the same usually, Br2, Cl2, something like that. If it's a hydrohalogenation, you're adding a hydrogen with somebody from group 7, like chlorine or bromine, like HCl, HBr, and those are, again, if you have it in words, that's basically what they're asking you to kind of do in that sense. In this case, we're adding water, which is a hydration reaction because we're adding water here. And once again, as I mentioned earlier, you will sometimes see some things written on top of the arrow, and those are, again, catalysts. They're not really sort of too much to worry about other than they're necessary for this reaction to sort of happen fast enough and not be really slow. But it really doesn't have any effect sort of on what you're going to draw in terms of your product. So H plus just means it's an acid as a catalyst. Again, for like hydrogen, you may see like PT written up there, which is platinum and stuff like that. But again, will not have any real effect on sort of what you're drawing. So what I did here is I just kind of redrew it so I could kind of just see the double bond, and I showed the hydrogens sort of that are directly attached to the carbons in the double bond. And remember, this is really the only place where you want to focus, and all you want to do is basically just copy it exactly the same, except just make it into a single bond. So we'll just kind of do that and just copy exactly the way it is. Once again, just going to turn double bond into a single bond. Bless you. Now, in this case, this is also sometimes referred to as an unsymmetrical addition. And an unsymmetrical addition means that you're not adding two things that are the same. Like in H2, you're adding two things that are the same, or Br2, you're adding two Brs. They're both exactly the same. And those are sometimes referred to as a symmetrical addition. So in this unsymmetrical addition, where we're adding hydrogen and something else, we do want to look at the hydrogens here, and the carbon on the left has one hydrogen to begin with. Carbon on the right has two hydrogens to begin with. So there is a difference in the number of hydrogens. So that means we need to follow Markovnikov's rule, which is the hydrogen goes to the one with the most hydrogens. So since the carbon on the right here had the most hydrogens to begin with, that is where we want to put our hydrogen. And then our OH would go on the other one. Again, making our alcohol here. And if we talked about naming it last time as well, 1, 2, 3, 4, that is 4 carbons, which is based off of butane, and it will become butanol because it's an alcohol. And we do also give the location of where the OH group is, and we do want to give that OH group the smallest number. So going 1, 2 in this direction will do that. So this is 2-butanol that we just made in that particular case. Any questions on any of that? Yeah. Instead of kind of breaking apart, putting the H's all over the carbon. Are you asking, could you just change that to a CH3? Yeah. And put a CH2 there and make it a single. You could. I just kind of drew it out so you could see it. But yeah, if you want to keep it truly sort of condensed, you could have just wrote it exactly the same. Add a hydrogen there, make it a single bond, and add a hydrogen at the end. And that'd be the condensed form. Yep. Other questions? You don't. I'll be happy to draw anything that looks right. Yes, that'll be good. Yeah. So, probably won't be too picky on what type of formula. Again, technically, if it does specify what type of formula you should draw, you should try to draw it that way. But if it just says draw the structure, then you can lay up any structure you like. That's appropriate. All right, question on these type of reactions. Yeah. It does. And it only matters, as I just mentioned, when you look at the double bond here and the number of hydrogens that are on each carbon to start with. are different. And in this case, they're different. The one on the left has one hydrogen directly attached to it, and the one on the right has two. And in that case, when they are different numbers of hydrogen to begin with, the hydrogen will always end up at the carbon that had the most hydrogens to begin with. So in this case, that would be this guy over here had the most hydrogens to begin with. If they were identical, numbers of hydrogens on the double bond in each of those carbons, doesn't matter. You can put it on either side. You'll end up with the same structure regardless. Yeah. What happened to you? Say again? I probably put a hydrogen instead of a OH there. That should have been there. There. I was thinking we were at an H2, I think, when I was drawing that. So yeah. So actually, this one would not get the extra hydrogen. He would just have the OH in that case. Yeah. Thank you. Other questions? All right. Then let's continue on and talk about another sort of class of organic compounds. And these are sometimes referred to as aromatic compounds. And aromatic compounds has a special sort of organic structure, which is known as benzene. And benzene is a six-member ring that has three double bonds in it. And it's C6H6. It also could do a resonance structure where those double bonds move to the other side and look like that. Although your book usually doesn't like to draw it like that. Your book just likes to draw just like a circle in the middle and stuff. So, and the reason for that is we talked about when we were doing bonding, those double bond electrons are moving around. So at any particular time, could look like the guy on the left there, or it could look like the one on the right. So to simplify, sometimes in organic chemistry, people will just kind of draw a little circle in the middle to indicate that those electrons are moving around. But it does have three double bonds. Even when you see it drawn with a circle, there's still, when you see this circle drawn, it is one of these sort of structures here, is basically what it is. It has the three double bonds still in it. And again, when we talk about benzene, we do sort of follow some rules for it, but there also are a number of sort of benzene sort of molecules that have these sort of historical names that are still used today. So, for example, on the left there, if you have a benzene ring with a methyl group on it, that is known as toluene. Now, if you wanted to sort of name it without sort of using the historical name, we typically will just kind of put the group and put benzene at the end of it. So this is sometimes called methyl benzene, yeah, because it has a methyl group basically hanging out there on the benzene ring, basically. If you have a benzene ring like you see here that has what is known as a nitrogen-containing group, this is an amine, that has a historical name known as aniline. And a benzene ring with an OH group is what is known as phenol. So those three sort of names are still used today, even though they're sort of historical names. They are definitely seen in a lot of places, so you probably will come across them along the way here. So toluene, CH3 group on a benzene, NH2 for aniline, and a phenol has the OH type of group. Yes, sir. I'm sorry, I missed the first part. What? Yeah, so yeah, you could use whichever name that you want with this, and we'll see some more examples here in just a second. But you should be sort of familiar with those because, like I said, books and stuff still kind of use them a lot sometimes, and they do kind of pop up, as you go through it and stuff like that. So as I mentioned before, a more sort of common way of naming these guys when we have things attached is kind of put benzene at the end of the name and sort of attach to groups and like normal. So if you have just one group attached like we see here, this is just going to be chlorobenzene, as obviously this entire thing is the biggest carbon chain and that's the benzene ring. This is two chlorine groups, right? So that is where the dichloral part comes into play. Obviously this entire thing is a benzene ring and the location here is 1 and 2. Now, when you have a benzene ring, because it does have technically those three double bonds that happen. If you remember when we talked about cycloalkenes, where you have a double bond, you have to number through the double bond, right? You can't go away from it. But because this actually has the three double bonds, it doesn't matter which way you go, you will always technically be going through a double bond. So you can just kind of go the shortest way to each of those groups to give the numbering. And it doesn't really matter in this case. So you go 1 and 2 here. And again, that's how we get our 1, 2. This is 1,3-dichloral benzene, and that is 1,4-dichlorobenzene. Now, if you had different groups attached, you would probably want to number alphabetically and give the kind of the alphabetical guy that would go first in the name, the smaller number. But that would be kind of the only thing you need to worry about. Now, with benzene rings and groups that are attached, sometimes there's also an older way of sort of naming them that doesn't necessarily use these numbers. The 1, 2 positioning of groups along the benzene ring is sometimes referred to as the ortho sort of arrangement, and that is sometimes abbreviated with just an O. So what people would sometimes do is not go 1, 2, they would just go ortho or O dichlorobenzene, and that indicates that it's at 1 and 2, those groups. The 1, 3 positioning on a benzene ring is sometimes referred to as the meta positioning, and that is also sometimes abbreviated with just an M. And again, instead of the numbers, they would say meta dichlorobenzene. And the 1, 4 positioning on the benzene ring is what is known as the para positioning, which again also abbreviated with a P. And again, in place of the numbers, sometimes people will use ortho, meta, and para. Again, another thing that kind of pops up with benzene rings a lot is those kind of descriptions, and they indicate basically the positioning. So 1, 2 positioning is the ortho, 1, 3 meta, and 1, 4 is the para positioning. Again, this is specifically around a benzene ring. So if you have a benzene ring, that is kind of where those guys sometimes come into play. Any questions on that there? So again, you can kind of see some of our names here. If we take a look at it, we have, this is the benzene ring that has the NH2 group on it. So that whole thing right there is that aniline sort of historical name. And since we have one more group attached there, this is going to be priority number 1, 2, and then obviously at 3. So that is again getting us our 3-bromol aniline in terms of his name. Once again, if you take this entire thing here, that is the phenol part of the name. Again, that historical sort of benzene with the OH. And once again, because that's kind of part of the main group, we're going to kind of give that the priority. And if we go counterclockwise in this case, that's going to give us some smaller numbers for our groups that are attached. And that will get us here 4-bromol, 2-chloral, and phenol. Phenol. And once again, I think we also talked about this last time. As you can see here, it is possible to have sort of the larger number come first. Again, we're going alphabetical based on the group, so that's okay if you didn't again have the larger number that comes first, even though alphabetically it should obviously go that way. And then obviously over here, we have toluene here with a lot of stuff attached to it. So that whole thing there is our, is our toluene. And obviously we have our couple of groups there. So we have our dibromo group and our chloral group, again, at the appropriate sort of numbering as you go through there. Any questions on those guys there? All right, so let's take a look at each of these here. We want to select the correct name. So if we take a look at the first one, that again is a benzene ring. And we have a chloral group attached to it. So I feel like I'm looking for something with those names in it. Remember as well as our first option here is, this is cyclohexane. Cyclohexane is the exact same shape, but no double bonds, right? So it's all single bonded, no double bonds, so no good. And I think this one should be a nice winner there. Chloral benzene. Again, here you do not need the number when there's only one group attached. Wherever that group is attached is assumed to be carbon number one, so you don't actually need the numbering. You only really need numbering when you have more than one group attached to sort of the ring. If we come back down to here, technically speaking, here, this is our benzene right there. That is again a methyl group. That is a methyl group. That means I got two methyl groups in this compound, which is a dimethyl situation. And in this case, probably clockwise here is going to give me the smaller numbers. Going counterclockwise is going to give me bigger numbers going in the other direction. And that looks like 1 and 3 dimethyl benzene. Yeah. By the way, that 1-3 positioning is also the meta positioning, right? We have 1 and 3 groups at 1 and 3 on the benzene ring, so that is meta. You could also call it meta dimethylbenzene. Dare I say, you could also call it toluene is in there as well. So again, a lot of times organic compounds do have multiple names for the same thing, kind of a historical name, common name, formal name. So sometimes you do come across 3 or so different names for the exact same thing. Yeah. Any questions on benzene? Okay, we are off to chapter 12, and we're going to cover some more organic groups: alcohols, thiols, ethers, aldehydes, and ketones. And a lot of these groups have oxygen in it. In fact, 4 of the 5 have oxygen in it, and thiols have sulfur in it. So we've got some other elements kind of coming into play: oxygen and sulfur in each of these guys. Um, so let's talk about the functional groups for each of these sort of organic compounds. So remember, the functional group is the part of the molecule that makes it a certain type of compound. Alcohol functional group is the OH group, so it has to have an OH group on it to make it an alcohol. Phenols here is what we just saw there are benzene ring with the OH, right? Thiols will have actually a sulfur hydrogen group. And ethers will have this sort of run: carbon, oxygen, carbon. So they'll have like a carbon, oxygen, carbon in it. And again, these are the parts of the groups that basically make these things: alcohols, thiols, and ethers. By the way, the other couple of groups that were on there is aldehydes. And aldehydes have this functional group. It has a carbon-oxygen double bond with a hydrogen, so that is the functional group for an aldehyde. And a ketone has a 3-carbon run, and in the middle carbon of those 3, you will find a oxygen double bonded to it, and that is how you could recognize a ketone. So again, being able to recognize these functional groups and these little parts of these molecules is really important to help you sort of think about, what type of group you're dealing with. And it also helps you with the naming part. It kind of puts everything, how things end and stuff like that. So you want to kind of look for those groups. In addition, as we'll be talking about throughout this chapter and others as well, pretty much everything happens at the functional group in these molecules. So when they do some type of reaction, it's all going to happen right there at the functional group. Is kind of the important part of the molecule. All right, so let us talk about naming alcohols, which we kind of jumped into in the last one when we were doing the hydration reactions. But just to remind you, again, the alcohol will have the OH group. Much like everything else in organic chemistry, we're looking for the longest carbon chain. The important part in this case is that longest carbon chain needs to have the OH group as part of it. So it's got to be kind of attached to that OH group. That's going to give you the base of the name, which will match those alkanes. And the difference here is we're going to go OL at the end of the name rather than ANE. Now, as we also talked about, the priority in terms of numbering the chain, the longest carbon chain, is the OH group here. So much like the double bond and triple bond gets the priority in terms of the numbering, here the OH group gives the priority in terms of the numbering. And always in organic chemistry, it's all about the smallest number. So we want to give the OH group the smallest number. Once you give that OH group the smallest number, any other groups that are attached are named accordingly in terms of the numbering. And the other thing that we talked about, obviously, is, at about three or more carbons, you need to give the number of the OH group on the carbon bond, right? So where that guy is located is where you need to give it. Obviously, for something like methanol, there's only one carbon, so you don't need to give the number. Ethanol, also, there's only really one place where you can put that OH group, either the left-hand side or the right-hand side carbon. And if you did, either case, it would always be carbon number one, no matter where you put it. So you don't need the number. It is when you get to our friend propanol, which is three carbons, that you get an option as to where you could put that. You could put the OH group, say, on the first carbon here. And obviously here we'll have something like this. And this is three carbons, which means is propanol. And here we want to give the OH group the smallest number. So right there, carbon number one, this would be one propanol. Once again, you could have your three carbons and put your OH group there in the middle carbon. I'll just do a condensed structure over here and add my hydrogen in there. Again, we have three carbons, which is propanol. And the OH group, though, now is at carbon number two. So this is 2-propanol. As I also mentioned last time and a second ago, another example of something that has like three different names. That is 2-propanol. This is also, if you remember, our isopropyl group, and it's an alcohol. So hence the name isopropyl alcohol is why it's called that as well, because it has that isopropyl group. And again, this is rubbing alcohol, basically, right? So, it's kind of common name, regular name, and, more formal name. So once we get to three or more carbons with the alcohol or the OH group, do have to give the number of it. Once you lock in the number of the OH group, all the other groups are numbered accordingly. Once again, if it is a tie in terms of numbering the OH group, then the next thing you want to look at is the groups that are attached, and you want to give the alphabetical sort of groups smaller numbers as you go through there. All right, so once you give that a name, why don't I just draw some crazy things and give those crazy things some names? Uh, do that. Why don't you also draw a couple of alcohols? Let's draw some type of alcohol. Let's do 2-methyl. Let's go underneath it. Uh, 4. Let's go hexanol. Try that. Why don't you draw cyclopropanol? All right, so give some names on the left, draw some things on the right. We'll hope for the best on all that. Okay, let's make this 3-hexanol. If I like that better or not, but we'll try it. Okay, let's take a look, see how you're doing. First one looks like 6 is the longest. You can get 6 straight across here. It has the OH group on it. By the way, you could have also went upwards here to get to 6. It doesn't really matter. So I can go 6 there. That is going to be hexane. It does have a OH group, which is going to make it hexanol in this case. We do want to give the OH group the smallest number, so just looking at it, we should probably number in this direction, and that will accomplish that. And that means my OH group is at carbon number 2, and that's going to be a 2-hexanol. And because I locked that into place, the one last thing that's hanging out there is a methyl, and that's at carbon number 5, and that would be 5-methyl 2-hexanol. Any questions on that one there? Yeah. Yes. So the functional group typically is the one that gets like the priority in numbering. So just like with double bonds or triple bonds, they get the priority. So here the OH group gets the priority. You always want to give it the lowest number. The only time it really won't matter is if you kind of go in both directions and it's the same number, then you could go to the groups next would be the next thing you want to look at. Yeah. Other questions? Okay, take a look here. Did I draw the same on this one? Probably did. One, two, three, four, five at least. That's good. So that's going to be pentane, and since we have the OH group there, pentanol. Again, location that OH takes the priority, so we're going to go in this direction, and that's going to be a 2 pentanol for the location of the OH group, and that puts my chloral group there at carbon number 4, so that is a 4 chloral 2 pentanol in this case. Yeah. Any questions on that there? Longest carbon chain here is the ring that has the OH group. And that is a 6-member ring, right? So that's based off of cyclohexane. Since it has an alcohol group there, that's going to now become cyclohexanol, OL at the end of it, right? Now, I do have a methyl group there, and in this case, the OH still wants to give the smallest numbers, so we're going to start numbering there to give it the smallest number it could possibly have. And obviously, if we go clockwise here, we're going to hit 3 for our methyl group is the smallest. So this is going to be a 3-methyl cyclohexanol. Yeah. Yes, sir. You don't need to in this particular case because it's part of the main chain. Yeah, so it's implied when you do cyclohexanol that it has an OH group, and because that's the functional group in this case, it should always have the smallest number. So it should always be carbon 1 wherever it's at. So if you turn this thing on its side and the OH group ended up over there, and the methyl group ended up over there, same thing. You're gonna start numbering where that OH group is at. Yeah. Other questions? All right, drawing. Let's see how bad I did here. We're going to go with hexanol in this direction. So we're going to go with 6 carbons. And OL tells me it's an alcohol, and the 3-hexanol tells me it's at carbon number 3. And again, since you're drawing, you could go in either direction for carbon number 1. I'm going to put my third one there, and that takes care of that. That means at carbon number 2, which would be 1 back, I'm going to have a methyl group. And now I can just really fill in my hydrogens here. So 3 for this guy. 2 bonds need 2 hydrogens. 2 bonds needs 2 hydrogens. 3 bonds need 1. 3 bonds need 1. And 1 bond needs 3. And again, that would be more obviously of a condensed formula that we got going there. If you're going to do line, same deal. 1, 2, 3, 4, 5, and 6. And again, at carbon number 3, an OH, and a little methyl group right there at carbon number 2 in that case. Yeah. Any questions on that one there? All right. Cyclopropanol. So again, cyclopropane tells me it's a 3-member ring, right? So that is a triangle. And OL tells me there's an alcohol group. Does it really matter where I put it? It doesn't matter. You could put it up on top. You could put it to the one on the right, the one to the left there. It doesn't matter. They're all the same. They're all the same structure. Just that guy turning around if you drew it. They're different places, basically. Any questions on any of those there? Okay. Yeah.
If you were to put the OH on group one, would you need to specify it's group one, or just put small?
You would, yeah. So basically, 3 or more. There's options of where it could be, and it is possible for it could be up number 1. So you do have to specify because there's multiple options where that could be. So yes, so yeah. Other questions? All right, a couple more here. Okay, let's take a look. So once again, look for longest carbon chain straight across here. Looks good. 1, 2, 3, 4, 5. It's got the OH. Once again, you could also go straight across and then come up to get the 5. And again, if you have the option, I would usually would just say take the straight one across. It's probably the easier move. We obviously have a methyl group hanging out there that's not part of it. So our 5 carbons here are going to be based off of pentane. So again, we're going to end up with a pentanol. More than 3 carbons here with an alcohol, we need the location of that double bond, and given it the smallest number is going to be number 2, so that's going to be a 2-pentanol and a 4-methyl 2-pentanol. Just kind of put that down there. Any question on that one there? Longest carbon chain that has the OH group is right here. That is, what is that? It is phenol. Remember, this is not cyclohexanol because it's got some double bonds. That is a benzene ring, as we were just talking about, that has an OH on it, and that is a phenol. So that is the main group there. And 1, 2, and 3, and that's going to be a 3-bromol phenol in this case. Yeah. Questions on those there? Okay, we're going to continue on. So obviously we're talking about alcohols here. Where'd my pen go? And we got into sort of the naming last time, and again, it does follow very similar to double bonds and single bonds as our double bonds and triple bonds in terms of how you name it. Just replace that with the OH group. Let's continue on. Ethanol, which again is ethyl alcohol. Um, that's the good alcohol, I suppose. Is formed from the fermentation of grains and sugars. Uh, there's also glycerol, which we'll actually see in a later chapter when we get into lipids. That's a 3-carbon group, and it has that OH groups there. By the way, alcohols are sort of soluble a lot of times in water, at least with that OH group. Remember, the OH group is a polar group. And it's more negative on the oxygen, more positive on the hydrogen. And again, if they do have an OH group in alcohol, which they should have, it usually helps with their solubility with something like water, which basically has the exact same bond. And that allows water and an alcohol, obviously, to hydrogen bond with each other and interact with each other. Usually, you're good in terms of solubility of alcohols with water up to about 5 carbons or so. And if you have more than that, then the solubility really does start to decrease. By the way, another thing that can help increase the solubility with water is having multiple OH groups. So having those multiple OH groups also increases the solubility of things just like with water. Ethylene glycol, as you can see there, that's basically antifreeze. And that's what you put in your car. And it works, actually does 2 things. It increases the boiling point of water so you don't overheat, and also decreases the freezing point of water so you don't freeze if you're in a really cold environment. So that's basically your antifreeze you put in your car. Let's talk a little bit about some other reactions that alcohols undergo. So we talked about how we make an alcohol, which is obviously from an alkene through a hydration reaction, we produce that alcohol. And really, a dehydration reaction is the opposite. In a dehydration reaction, we're removing the water that we put on. So in a hydration reaction, we put water on, and when we dehydrate it, we take water off. So if you remember, as we just saw there, we went from an alkene plus water gives you an alcohol in a hydration reaction. In a dehydration reaction, we start with an alcohol and we actually remove water and get the alkene back, plus the water comes off. So we're basically going to take the water off. So if we had an alcohol like we see below there, and we add maybe some acid and some heat. By the way, heat is sometimes also just abbreviated with a triangle. So if you see a triangle on top of the arrow, that usually implies heat was sort of involved in it. And it dehydrates. So the deal is, just like we put water on, the H goes to 1 carbon, the OH goes to another. When we take the water off, we do the same thing, H from one carbon, OH from another. So we take the water off the same way that we put it on. And just like everything else, if we were drawing this, nothing much is going to change. So other than the water we're taking off, everything else there that I just highlighted stays exactly the same. So you basically just redraw everything there except for the water part. And if you redraw everything there except for the water part, you'll end up with something like this. Now, we obviously will have water that comes off as well. The problem, though, is my carbons where I took the water off is now short a bond, right? And when we put the water on, we take the double bond off. When we remove the water, we put the double bond back on. So we can just put the double bond back on where we took the water off of, and we get our alkene back. So you can think of a dehydration reaction, which it really is. It's really just the opposite of putting the water on. Basically, just going to take the water off. And where you take the water off, slap a double bond back in that place where you took the water off, and you'll get back to your alkene. Any questions on that there? Now, before we get into that, let's maybe find somewhere here. Maybe. I'll do it here. Now, if you remember when we put water on, if the double bond had different numbers of hydrogens, it was important as to where the hydrogen went and where the OH went. And that can also happen in a dehydration reaction when you take the water off. So you take the water off in a reaction such as this. Let's do this actually. And maybe I'll do this. And I'll do this. Okay, we have this, and we're going to dehydrate this thing. Let's go underneath. Again, eat it up. So that is going to actually take off water. And for sure, what's going to come off is the OH has got to come off to get rid of the water. But in this option, I actually have two choices as to where I can get the hydrogen from. If I look at the carbon to the right, I could take a hydrogen from that one. And if I look at the carbon to the left of that OH group, I could take a hydrogen from that one. So in this case, you do have options as to where you could actually take the hydrogen from. In the previous example, we didn't have that option. There was just one carbon next to it and there was nothing else, so you had to take the hydrogen from that one. Now, in this case, what happens is opposite of how we put the water on. So when we put the water on, right, the hydrogen goes to the one with the most hydrogens to begin with. If you have a situation like we do here where we look at our two possible carbon options as to where we could remove a hydrogen from, and they have different numbers of hydrogens. So this one has 3 hydrogens, right? And this one has directly attached to it 2 hydrogens, right? We actually take the hydrogen from the one with the least number of hydrogens. So when you put on the water, most hydrogens is where the hydrogen goes. If you have an option and you're taking water off, you take it from the one with the least. So we would actually want to take a hydrogen off of this carbon here. And if we do that, nothing else is going to change. So we're going to end up with something that looks like this. And we will get the water that came off. And at this point, we will need to put a double bond right there. And I feel like I was missing a hydrogen there to begin with there. Let me fix my original picture. Lost my hydrogen. There it is. That guy should be there. So I'll put it back in. Now we're good. So we'll just put the double bond right there. So if there is 2 carbons you're looking at, and you could take a hydrogen from each, and there's different numbers, we take it from the one with the least. And again, that's basically the direct opposite of when we put it on, the hydrogen goes to the most. So there are backwards reactions of each other. So that's why you kind of do everything backwards as you go that way. Any questions on dehydration reaction? So obviously a dehydration reaction, as we see here, will yield us an alkene, a double bond. And obviously an alkene with water will yield us an alcohol. All right. The next type of reactions we're going to talk about with alcohols are oxidation and reduction reactions. And oxidation reduction reactions have three types of definitions. Oxidation, as we talked about earlier on in the semester, deals with losing electrons. Reduction deals with gaining electrons. But since these are organic compounds, we really don't deal too much with the electron definition of oxidation and reduction. We actually deal with the hydrogen and oxygen definitions of oxidation and reduction. So if something is oxidized, it will also gain oxygen as you go from reactants to products, or it can lose hydrogen as you go from reactants to products. So those are two definitions in organic chemistry. These are really the definitions we look at for oxidation reactions. Reduction is the opposite. It can lose oxygen as you go from reactants to products, or it can gain hydrogen as you go from reactants to products. And again, these are in organic chemistry, the two definitions of reduction that we see. You really don't see too much at all ever, usually about electrons and oxidation reduction when you're doing organic chemistry. It's all about the hydrogens mostly. And then if it's not the hydrogens, then it's about the oxygen, either gaining or losing. Now, the other day as well, we talked about classifying alcohols. And remember, we could have a primary alcohol, a secondary alcohol, and a tertiary alcohol. And when you're deciding that, you want to look at the carbon that is attached directly to the OH and really how many carbons are directly attached to it. So in this case, this would be a primary alcohol as there's just one carbon directly attached to that guy. If you had the OH here and you're looking at this carbon and it's attached to two carbons, that would be a secondary alcohol. And if you had the carbon that had the OH group and you looked at it and it had 1, 2, and 3 carbons attached to it, that would be a tertiary alcohol. So we have primary alcohols, secondary alcohols, and tertiary alcohols. And these alcohols do go through oxidation and reduction reactions to produce sometimes other organic compounds. And remember that they always occur together. So if you have an oxidation, usually something is getting reduced along the way. So let's talk about each of these. Let's talk about a primary alcohol. So if we have a primary alcohol, let me just draw one out here. We'll go with this one. I'm just going to kind of fully draw it out, I think. All right, so if we take this primary alcohol and we do an oxidation, which by the way is sometimes just symbolized by that little kind of symbol right there. So if you see brackets with an O in it, it means, hey, do an oxidation reaction. So that is, again, a symbol for it. This, again, is a primary alcohol because when we look at the carbon that has the OH group attached to it, it is attached directly to just one other carbon in this case. So when a primary alcohol goes through an oxidation reaction, it will basically follow the definition of it will lose H2. So it's going to lose hydrogen. And that, again, is a definition of oxidation. Now, how does it lose hydrogen? Well, the way it loses hydrogen is always this way. It basically, 100% of the time, will always be the hydrogen that's attached to the O in the OH group. So you're always going to lose that hydrogen that's attached to the OH. And now the other hydrogen is going to come from the carbon that the oxygen is attached to. Your choice, whichever one you want. You can take either one. You're going to take out one of those. And that is going to give us the H2 that's going to come off here on the other side. Now, just like everything else that we've been doing, and if you got to draw something, I should just copy this thing exactly the way it looks. I shouldn't get fancy with it or anything like that. I should just copy exactly the way it looks. And frankly, I shouldn't think too much about it other than copying it exactly the way it looks. Obviously, the only thing I'm not copying is the two hydrogens I took off, right? Now, at this point, I'm pretty much 99% of the way done with my structure. The one problem that you might see is the carbon and the oxygen technically are short a bond. So if you remember, every time we put a bond on, we talked about earlier, you have to take off two hydrogens, right, to make room for that bond that you put on. So when we put a double bond on, you got to take two hydrogens off. When you put a triple bond on, you got to take another two hydrogens off. So in this particular case, since we actually took off two hydrogens, we actually need to put in a double bond, and the double bond always ends up right there between the carbon and the oxygen. 100% of the time, no matter what it looks like anywhere else in that molecule, that's the only thing that changes. So you're basically going to remove two hydrogens and add a double bond. And that will always be the case in this case. By the way, it is organic chemistry, and typically they don't show the non-bonding electrons that are still there on oxygen, and it still has this completed octet. But usually, just for simplicity, they don't kind of show those dots and stuff. But that oxygen up there is like a normal sort of double bonded oxygen. It does have those non-bonding electrons, which does give it obviously the 8 electrons that it needs. Now we go from a primary alcohol in this case, and we oxidize this guy, and we get a new organic compound, which is known as an aldehyde, which has that functional group of the carbon-oxygen double bond and the hydrogen. And dare I say, it's right there at the end of the molecule, right here. That is the aldehyde group, yeah. By the way, if we needed to name this, maybe not so original here. The number of carbons we got going on there is 2 carbons. That's based off of ethanol or ethane. And this becomes ethanal. It's actually Al at the end, not like the alcohol, OL. It's Al here. And that is what is known as ethanal, which is a aldehyde. Yeah. Any questions on that there? By the way, if you take a primary alcohol and you oxidize it once, you get an aldehyde. But if you take that aldehyde that you just made, it could also continue to go through another oxidation. Now, the first oxidation we did to get to the aldehyde was we removed hydrogen. When it comes to the second oxidation, what we're essentially going to do is the other definition of oxidation. We're going to actually just add oxygen. So we're going to add some oxygen here. So on this one, we're going to add oxygen. And oxygen always ends up right there, right next to that hydrogen. So the oxygen gets there. And once again, nothing changes. Looks exactly the same as it does on the left, other than when we get to the end, we're going to insert here the oxygen. And I'm going to make an OH group there at the end. And that is another type of organic compound. This is what is known as a carboxylic acid. A carboxylic acid has this as the functional group, a carbon-oxygen double bond, and an OH, which once again is what you see here. And that is the functional group there for this particular guy. I know you want to know the name, so why not? Let's talk about the name here. So this is also still 2 carbons, so still based off of ethane, but this is a carboxylic acid. So the way we name carboxylic acids is we put oic acid at the end of the name. So this is what is known as ethanoic acid. So you drop the A and E from the ethane and put oic acid, and you get ethanoic acid. That, by the way, is also known commonly as acetic acid. Yes, also known as like the major component of vinegar. Yeah, and that is ethanoic acid. So if you take a primary alcohol and you do an oxidation reaction, you will take off two hydrogens and end up with an aldehyde. That guy could then further oxidize to a carboxylic acid. By the way, as we'll talk about maybe a little bit later on, if you head in the opposite direction, by the way, here, whoops, where'd it go? This guy does have two hydrogens that came off. If you kind of head in the opposite direction and you started with the carboxylic acid, you could go this way, which would be a reduction reaction and reduce it back to an aldehyde. And if you have the aldehyde, you could go this way and reduce it back to an alcohol. So it can go in both directions. Oxidation going to the right and going backwards is just the opposite reaction, which is the reduction reactions that occur along the way, where you would removing the oxygen you put on and also adding hydrogen as you go back the other way as well. Any questions on a primary alcohol? Let's take a look at a secondary alcohol here. Uh, how do I want to do it? Maybe I want to do that, I think. All right, so if we take a look at this one here, which once again is a secondary alcohol, and again, the secondary alcohol is determined by looking at this carbon, and it has 1 and 2 carbons directly attached to it, so it is a secondary alcohol. And we're going to send this thing through an oxidation reaction. And as you might guess, what two things should come off here? The two hydrogens, just like it did previously. So again, we're going to take the H off of the O. And the only H that's there now to that carbon that's attached to the O is that one. And again, that is going to give us our H2 that's going to pop off there. Now, again, I'm just going to redraw this exactly the same way, except I am going to take out those two hydrogens. So this looks exactly the same. And I got me an O over there, right? And just like we did on the other one, what should I put between the carbon and the oxygen? I'm going to put the double bond. Once again, double bond always ends up there. Yeah. So going to remove the hydrogens in both cases and double bond between the carbon and the oxygen. Always don't think about it, just do it. Yeah. So just put the double bond there and you'll have the right structure. As you probably could guess, another new organic compound. So this is what is known as a ketone. And a ketone has a carbon, 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 3 carbons in a row run. And that center carbon has the double bond, which is what you see right there. That is 1 carbon, 2 carbons, 3 carbons, and the double bond happening right there in the middle is your functional group in this case. Now you may be asking what the name of it is. I know you're not. But here we take a look at it, and we got 3 carbons, which is based off of propane. So ketones end in ONE. So instead of propane, this becomes propanone, ONE at the end, yeah? So this is propanone, which is a ketone. And that is what you get when you oxidize a secondary alcohol. This ketone will not oxidize any further. So nothing, unlike the previous one where you could oxidize again, you're done at the end of this deal. So it will not be able to be oxidized any further. By the way, if you head in the opposite direction, starting on the right-hand side and going backwards, that is the reduction reaction. The opposite reaction is going to occur. You're just going to throw those H2s back on, that double bond, basically, and you'll get back to your alcohol. Any questions on a secondary alcohol there? Now let's take a look at a tertiary alcohol. Just need that. that. And here we have a tertiary alcohol. And once again, it is a tertiary alcohol because we look at the carbon that's attached to the OH group, and it has 1, 2, and 3 carbons attached to it. So a tertiary alcohol it is. We're going to oxidize this thing, which means we're going to remove our hydrogens. So I am going to take the hydrogen here, and when I get to the carbon that's boxed there in the middle, does it have any hydrogens? It does not have hydrogens, and that's a problem if you want to remove H2 and you're kind of missing a hydrogen. So because it does not have that second hydrogen that is necessary here, no hydrogen there, that means you get a no reaction. You cannot oxidize a tertiary alcohol because it is missing that second hydrogen that is necessary for that reaction to take place. So to summarize our alcohols here, if you take a primary alcohol and you oxidize it once, you get an aldehyde. If you take a secondary alcohol and you oxidize it once, you get a ketone. If you take a tertiary alcohol and you oxidize it, you get nothing. But the tertiary alcohol is still staring at you at that point. Yeah. Any questions on that there? All right. So again, it doesn't matter what things look like. That is the deal. So why don't you try one here? Let's just do. Uh, all right. Draw the product of this. Why don't you draw the product of this? And why don't you draw what you get off of this deal? All right, so let's take a look. So once again, once you see you have an alcohol, you see it's going through an oxidation. Just need to remember basically those two things. We're going to remove H2, and between the double carbon and oxygen, going to lay up a double bond, and that's all you got to do. So clearly here, we're going to look at the hydrogen always that's attached to the oxygen is going to go, and again, the hydrogen that's attached to the carbon that's attached to that oxygen. And in this case, we only really have that one option, which is right there. That's going to give us the H2 that's going to pop off of that thing. Once again, at that point, I pretty much could redraw what I got going on over there, except for the two things that are circled. So without thinking too much, just going to kind of copy what's over there and exactly the same. Nothing else is going to change. So I just took off the H2. Now I need to put the double bond on, and now I am done, right? I have now just made a ketone in this case. And here we have a ketone. That is 1, 2, 3, 4 carbons, and ONE is a ketone, so a butanone. Sometimes people might put a 2-butanone, but probably not in this case. Any questions on that one there? All right, same thing on the next one. We've got an alcohol, we've got an oxidation, so going to remove H2, always the hydrogen from the oxygen. And in this case, we have an option of which hydrogen we want to choose from the carbon. It doesn't really matter which one you want to choose. So I'm just going to take that one off. And again, you could have took the bottom one off too. It doesn't really matter. And again, at this point, we're just going to copy what's there. So I wish I didn't draw it out like that. I can kind of start over here a little bit to try not to run out of room. All right, we're going to go that way. We're going to go that. I should have done condensed. All right, we'll try that. Almost. There we go. And then obviously here, we're not going to draw the hydrogens we removed. So that takes care of the first part. I removed the hydrogen. Now the second part is double bond me up a carbon oxygen, right? Right there, yeah. At this point, I just made an aldehyde. And that is this group right here. Carbon oxygen double bond with a hydrogen is the aldehyde right there, sitting on its side. And that is 1, 2, 3, 4, 5 carbons. So 5 carbons, that's an aldehyde, is based off of pentane. But instead of ANE, we're just going to put AL at the end of it, and it's going to be called pentanal, not to be confused with pentanol, which is an alcohol. OL, alcohol, AL, aldehyde. How do you remember that? I don't know. Alcohol ends in OL, yes. Aldehyde ends in AL, or starts in AL, right? So aldehyde, AL, yes. So that is the way that you kind of do that. Any questions on that one there? All right. By the way, my first alcohol up there was what type? A primary, secondary, tertiary? This guy up here this was a secondary alcohol, right? And that is why we ended up with a ketone. This guy down here is a primary alcohol, which is again why we ended up with the aldehyde. We could, if we wanted to, oxidize this guy one more time to get to the carboxylic acid. Once again, if you did that, you're just dropping an O right there and everything else stays the same, and you'll make that carboxylic acid. But now we come over here to this one. This is what type of alcohol? Primary, secondary, tertiary? None of the above? All of the above? Some of the above? The question is, what type of alcohol is the bottom one? Two? Okay, I agree with you, by the way. You can say it louder. It's good. So it is a secondary alcohol. So we're looking at this carbon, which is right here, that is attached to the OH. And there is a carbon right there, right? And it's directly attached to it. And there is a carbon right there that is directly attached to it. This is a secondary alcohol. Yeah. Which, by the way, the helpfulness of knowing that is when I oxidize a secondary alcohol, what do I end up with? I end up with a ketone, yeah? So what happens in this case is the exact same thing. We're going to remove the two hydrogens. But although you may not see the second hydrogen, there is a hydrogen hanging out right there because that carbon only had 3 bonds, right? Which means, although not drawn in line structure, there is actually a hydrogen right about there. So we're going to remove these hydrogens. Going to draw it exactly the same with those hydrogens removed and my oxygen. And like normal, my second step is to put a double bond right there. Yeah. That is based off of cyclohexane, right? And it's a ketone that ends in ONE. This is what is known as cyclohexa ONE, hexanone. Yeah. So that is cyclohexanone, which is a ketone. Yeah. And if you can't see the ketone group, once again, the ketone group is right here. This is our 3 carbons right there, and our double bond happening right there with our oxygen. And again, that is where the ketone group is. 1, 2, and 3 carbons right there. Yeah. Any questions on those there? So just to finish up here, talking about sort of the reverse reaction, just to kind of touch upon it. If we had our primary alcohol, which we did there earlier, in an earlier example, I think we did this guy, and we oxidized it, and again, we took off our hydrogens, and that gave us our aldehyde here. Now, if we wanted to do the reduction reaction, which is going in this direction, if we wanted to do sort of the opposite of this reaction, which is the reduction reaction, we would start with our aldehyde here, and this is our primary alcohol. So if we started with our aldehyde, And when we're going to do our reduction here, that basically is the addition of H2. So we're going to add H2 back in, basically, yeah? So remember, when we oxidize it, we take the H2 off, and when we reduce it, we're going to throw the H2 back in. If you had to take a wild guess, where would the H2 be added to? Right here, yes. So when we had just a regular alkene, if you remember, right? And we have just a regular alkene, and we got this still. And we add hydrogen to it. We do what with that double bond? We make it a single bond to make room for what's coming in, right? And then what we do with that hydrogen is we put one on one side and one on the other, right? And maybe not surprisingly here, the exact same thing happens at the double bond, right? So we would actually do the exact same thing here. We cannot put those hydrogens on right now because everybody's full. Everybody has 8 electrons, but we need to make room for it. So just like we did down here with our alkene, we're just going to turn that double bond into a single bond if we're going backwards. Everything else stays exactly the same. So we're just going to draw this exactly the same. We're going to turn our double bond into a single bond to make room for those hydrogens coming in, the exact same way we did down here with our alkene, and we still have that hydrogen at the end. Now, just like when we put it on with the alkene, we put that hydrogen on, or these hydrogens, and I'll just draw them blue so we can kind of see them. One hydrogen is going to go to one side of where the double bond was, and the other one goes to the other side of the double bond. And what did I just make there? That is now my alcohol, yeah? That is now my primary alcohol I just got back from my aldehyde, yeah? So that is this reaction, basically reversing the oxidation. The reduction gets you back to your alcohol. So if you oxidize the primary alcohol, you get an aldehyde. And then if you reduce an aldehyde, you get back your alcohol. So they, again, they are direct opposites of each other. And it happens the same way as it does with an alkene. You just take the double bond and make it a single bond. The same thing happens when we looked at our secondary alcohol. And again, this is our secondary alcohol, which gave us our ketone when we oxidized it. And our hydrogen came off. And again, these two hydrogens, just like we talked about earlier, you could also do the opposite reaction, which is the reduction, and get back your alcohol. And it works the exact same way. If you started with your ketone, and you add your hydrogen back in, what is the first thing I should do here? Make the double bond into a single bond. And again, everything else is going to be exactly the same. And now we have basically made room for our hydrogens to come in. And I'll draw these in as black hydrogens here so we can see the difference. And just like how we take them off, that is exactly how we put them back on. And now we got our secondary alcohol back from our ketone. And again, this is our reduction reaction going in that direction. So oxidation, hydrogens come off. Reduction, you throw them back on in the same location. And you can basically reverse the reaction, basically what you just did. Any questions on that there? Obviously, a tertiary alcohol doesn't do anything, so you can't reduce it either because you can't oxidize it, so there's no reduction that occurs with that as well. Question on oxidation reduction reactions of alcohols. Yeah. 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 So again, remember basically the definition of oxidation, or one of the definitions is that you lose hydrogen. You could also gain oxygen. And a definition of reduction is you gain hydrogen and you lose oxygen. And those are really the two definitions of oxidation reduction that's used with organic chemistry, because it's all about nonmetals and nonmetals. So there's not a lot of looking at electrons being gained and lost because there's not really transfer of electrons. Everybody's sharing electrons. So we look at the either gaining or losing of hydrogen or oxygen as to sort of what is going on in terms of oxidation reduction with organic compounds. Other questions? Yep. All right, let's lay that up for today.